right. Hi, it's great to be here. This is interesting for me. I was last on a RustConf stage in 2019. I was giving a similar kind of talk. Lots happened in between now and then. A lot of updates, a lot of things have changed in embedded Rust. So I thought it'd be nice to come back and give you a bit of an update. Yes. By the way, if you think the slides look kind of retro and crunchy, yes, I used PowerPoint 95, the best PowerPoint, to design them all. Literally not kidding. Right, so here's the agenda. We're going to a little introduction about me. We're going to set the scene, explain what we're talking about. And I want to introduce the Raspberry Pi Pico, this great little microcontroller. Rust works great on it. And then I want to show you some code. I've had some grief from people in previous talks. I don't put enough Rust code in my talk, so there's at least like one slide with some Rust on it. And then hopefully the demo gods will shine upon us and we'll be able to turn this thing on and we can do some demos when we finish up. Start my little Tom here. All right. So my name's Jonathan Pallant. You can find me as the JPster online. I teach Rust at Ferrous Systems. I like making embedded things. I can't help myself and I like telling people about them because I want to encourage more people to do embedded Rust. And what I want to talk about today is about video. I love the idea of video for the same reason I love embedded systems. Embedded systems are about writing some code, doing a thing on the machine, and then a physical, real-world action happens. The light comes on, the motor spins, the door opens, whatever it is. It's just a really tactile way to interact with the computer. And I discovered video is just an extension of that. If you're designing the circuitry and the software that makes the video signal, then you've done a thing on the computer and you can see the output. And if you get it wrong, you can't see the output because, you know, it's jumbled and jittery and all manner of things can go wrong. I've seen them all. And in particular, I want to talk about generating VGA video. It's an old-fashioned standard. It's a great piece of clip art from the PowerPoint CD. These kind of old-fashioned monitors. And that's really where we need to start telling our story, because those old-fashioned screens kind of set the standard for really how we still do video today. So it's a cathode ray tube, those old-fashioned monitors. It's a big piece of glass, it's a vacuum inside, and you fire an electron beam towards the front, which is coated in a material that will fluoresce, and then we steer the beam around using some magnetic coils. It is literally a cathode firing a ray of electrons inside a big tube. And that's important because it kind of constrains what we're doing. We need to fill the screen, but we've only got one point of light to do it. So we use the magnets to steer the point of light left and right across the screen. When we get to the end, we have to return the beam back to the left-hand side so it can scan again. And so we're chopping up our two-dimensional display into this kind of one-dimensional signal. And the timing for this is crucial, because if you get it wrong, those old-fashioned displays, the beam isn't in the right place and you can't see the picture. But if you've got a modern system using HDMI, for example, the same kind of thing still happens. You are still sending the pixels one at a time, left to right for each scan line, and then there's a little kind of pause in the signal where the virtual beam makes its way back to the virtual left-hand side of the screen. I mean, that's not really what's happening, but it's all still baked in to the standards. And of course, we don't want to send a monochrome signal, we want to generate color. So we use the only three colors known to biology, red, green, and blue. No other colors exist. And we send three unique signals. And we can see we've got a sort of a sample of various bits of video data here. There's kind of a wiggly one. Let's imagine some kind of colored image going on, and the colors and brightnesses are varying. And then the one that's a solid block, well, that's going to be a solid white line, because all three colors are wound up to maximum all the way across. And you can see the little pauses in between. And at the bottom of the screen, you can see the little sync pulse. This is a little digital signal that basically tells the monitor, hey, it's time to start swinging the beam from the right over to the left and just drop it down one line. So if you want to generate video with a microcontroller, you have to produce these kinds of signals. The standards go back a long time. We first saw this kind of video at these resolutions 1987. I was about 6 years old, and the video graphics array from IBM was released. It wasn't in the first PC. PCs have been around since 1981. They only had much more limited sets of colors, more limited resolutions for the first kind of 6 or 7 years of their lifespan. And this is where we get the classic 640 by 480 resolution from. That came with IBM in this standard. So that's 640 by 480, that's guiding what we need to generate. If we don't generate our signals according to these timings, we won't get a picture. 525 lines, that's curious. I said it was 640 by 480. Some of the lines are invisible. They're basically off the bottom, and that covers the amount of time required for the beam to get from the bottom of the screen all the way back to the top. These are known as the vertical blanking interval. And there is also a horizontal blanking interval. It's just a blank period of signal off the edge of the screen while the beam swings back to the start. And we have to generate 25,175,000 visible pixels per second. And if we don't, then you won't get a picture. You have to keep refreshing the pixels constantly, otherwise you don't get a display. There's also a 400-line standard for backwards compatibility reasons, but if you ever wondered why Doom runs at 70 Hertz or 35 frames per second, it's because they're in the 400-line mode. It's exactly the same number of pixels per second, they just traded some vertical lines for frames per second. So, the Raspberry Pi Pico came out in 2021. This board costs $4. The main processor on it costs under $1. You can get it for 75 cents. And really, it's an astonishing amount of computing performance for that price. And we can program it in Rust. We don't need any C code. We can do the whole thing in embedded Rust, top to bottom. So within this chip, you get 2 ARM processor cores. It's very interesting from a Rust point of view, because we can now have 2 processors running the same code. It's like having 2 threads. Of course, Rust doesn't really understand what a thread is. It has this idea of send and sync, and all of those things apply on this embedded system with 2 cores, just as they would if you were, say, running on a Mac laptop and you had threads. We have 256K of RAM, which on the one hand is a lot, because microcontrollers normally only have like 32K, but on the other hand, it's nothing compared to like a desktop machine. So you have to be pretty efficient with how you design your data structures, with how you design your code. You can connect an external flash chip, that's where the program code lives, and then we've got these fancy little things called a PIO block. They're specific to this particular kind of microcontroller, and we're going to see those later because they help us generate the video signal. Now, to get video out of this microcontroller, it doesn't have a video generator circuit in it. That's not what it was built to do. We just wire it up with some resistors. You can do this on a bit of breadboard. The digital to analog converter is just a handful of resistors to mix the digital signals together and get yourself the analog signal you need to go out to the screen. So the job to get this sort of project to work, we need to store some text in memory. We then need to convert that text into actual colored pixels that we can display with 12 bits per pixel. We have to send it all out the I/O pins. We've got to get all the timing correct. And based on the clock speed of the processor, I've got about 6 clock cycles to do every pixel. And that's all I've got. I can't use more than that. If I use more than that, I don't get a picture. Ask me how I know. Spend a lot of time staring at monitors going signal out of sync. Technically, this chip can only run at 133, runs at 150 just fine. Some people run it at 250. So for our timing signals, as we saw, we need to wiggle the little pulses. There's actually 1 pulse for the horizontal and 1 for the vertical. You've got to get them all both going, get them in sync. Again, if they fall out of sync, you don't get a picture. So what we've done, what I'll be able to demo, is a text mode. 80 by 25, kind of the classic PC text mode, 16 foreground colors and 8 background colors, because that's how IBM designed it. So we can have sort of text on screen, and we can convert that into pixels in real time. There are also a couple of bitmap modes. But the bitmap modes on the RP2040, I can have either 2 or 4 on-screen colors. I tried really hard to get 16 on-screen colors working, but I just didn't have enough processor time. Any LLVM experts want to explain to me why I've got a constant load from the literal pool in the middle of my hot loop? Please come and explain to me, because I don't know why it's there, and it's kind of ruining my timing. So this is what the text mode looks like. I think we get it all on the screen there, perfect. So we see we've got colors going on, we've got this beautiful font, took that from FreeBSD. So all the code I wrote is GPL, it's open source, you can find it online at these various GitHub repositories. It's part of an operating system I wrote, so there's different crates for kind of different layers in the stack. But the one we're talking about today is called the Neotron Pico BIOS. It's kind of the hardware abstraction, that's where all the video code lives. So if we want to have sort of one piece of code putting text into memory, that is the text we wish to display, that's where our printf, our print line will go into this kind of shared memory. And then I've got 2 processor cores, so the other processor core is then reading it out and converting it into graphics. And this used to be a static mute, and for reasons known only to themselves, the compiler people tell me this is not allowed. They were so upset with it that they added warnings to the compiler and all my code stopped building. So fine, we'll just use an unsafe cell. I don't care, same thing as far as I'm concerned. And we've got this array of glyph attrs. They are a combination of a glyph, that is the choice of character, and the attributes, that is the foreground and the background colors. So I wrap it in an unsafe cell, and then I've got some nice methods. And actually, this buffer ends up being shared between 2 different programs. The BIOS is one program, the OS is the other. And so I have to make things repr so I can share them across the 2 different code bases. But basically, the OS can put text into this buffer, and then the BIOS reads it out and colorizes it. And here's my hot loop, hence the flames in the corner. This is the thing that happens 6 clock cycles per pixel. Yes, I'm doing pointer maths because I can't afford bounds checks, and I wasn't able to convince the compiler to take them away. But basically, we have our row pointer. This is the start of our text buffer, the particular line of text we want to display. We're going to offset it by the column we're in. We can go across column by column. We then look up in the font. I multiply by the font height, so I jump to the correct place into the bitmap. And ultimately, what I end up with is you need to display these 8 pixels. Some of them are foreground and some of them are background. And I have another piece of data which says your foreground color is blue and your background color is yellow. And then I need to colorize the pixels. I need to go blue, yellow, or however. And that's the thing that takes the time. And the thing I worked out was you can cheat and do a lookup table. So I've got this table object here, and I'm passing it the pixels, 2 pixels at a time, and the attributes. And the lookup table is a great way of getting performance out of your embedded systems. Basically, I've arranged the table in order, and so I calculate the table index by taking the foreground color, multiplying it by 64, and then I take the background color and I multiply it by 16, and I take the pixels and I add them all together, and that just gives me an index, and I just read 2 colorized pixels out of the table. And that I can do fast enough. There's not many systems who are able to do kind of the full 80-column color video, but with this kind of lookup table, wastes about 2K of RAM, but it makes the whole thing possible. So there's a takeaway. Recommend lookup tables if you really need performance. But then we need to get the pixels out of the system, and this is where those PIO blocks help us out. The PIO block is like a little tiny processor that has maybe 7 or 8 different instructions. It can push things out of the I/O pins, it can read from a little FIFO, and it can do little loops. And that's all it knows how to do. And we have to program it. And that program needs to be compiled, and that compiled program needs to be loaded into the PIO processor. In the C developer kit that Raspberry Pi provide, there's a standalone compiler, and then you compile your PIO assembly code, and you get a file out, and you have to include that. But we've got macros. So the great people at the RPRS project wrote a macro which can assemble PIO assembly. We don't need to use the C SDK at all. The macro can do it all. So this code is interpreted by the macro and just converted into the binary instructions, and I can load them straight into the PIO processor. So nice having the code in my Rust source file and not having to kind of store it out in a different assembly file. And then there's a second program which handles the timing. I feed it special configuration values, and it produces the horizontal and the vertical pulses, and it gets all the timing perfect. And this one, I can get it to generate an IRQ. That's the bonus instruction that I can feed in, and that IRQ then triggers this program to go and display the next line of video. So they always stay in sync, no matter what the processor is doing, which is super important. All I've got to do is generate the colorized pixels fast enough and then get them fed into the FIFOs. So the whole thing ends up looking like this. We've got our two processor cores, Core 0 and Core 1. Core 0 is running the operating system effectively. That's the thing doing the print lines. That will work out what Unicode text you've asked to display, produce all of the various glyphs, and will save them into that shared buffer. Core 1 is running routines from the BIOS, and it will pull those characters and those attributes out of the text buffer, and it will colorize them with that hot loop algorithm we saw, and it will save those colorized pixels into one of two scanline buffers, an odd one and an even one. And at any given time, Core 1 is filling up one of those buffers, while the other one is being played out to the screen. And at the end of every line, we just swap. We can play out the one we just drew previously and start filling in the next one. And then we use these blocks called the DMA engines, and they can move data around in the background. They're very powerful, the DMA engine. It's like hardware accelerated mem copy. You just say, hey, I would like you to copy from this pointer to that pointer, and I would like you to copy this many things. And it will just do it in the background. Unfortunately, that is like the literal definition of shared mutable state, and it's the thing that the Rust compiler people tell me is bad. So programming the DMA controller is kind of an interesting exercise, but we have kind of Rust abstractions to make it work. The DMA controller then copies it into the PIO processors, which then play it out through the I/O pins. So that's the plan. Would you like to see a demo? Who wants to see a demo? All right. Now we had some technical problems. I've had a lot of technical problems over the last couple of months because, as I explained, the RP2040 can't do 16 colors on the screen at once. However, this entire slideshow is being presented for the Neotron Pico because that is not plugged in. But this is a curious thing because there are definitely 16 colors on these slides, and I wasn't lying to you. This doesn't work on the RP2040, but I'm not using an RP2040. The RP2350 came out a few weeks ago, and I was able to port all of the code to run over on that CPU instead. And that CPU doesn't have two Cortex M0s, it has two Cortex M33s. And it runs exactly the same instructions, but some of those instructions now take fewer clock cycles than they used to, which means basically the exact same code now does complete with only 6 clock cycles per pixel. So I've got a quick demo for you, but there's the URL. You can go and find all the source code, but I mean, I'm not kidding. We've got a computer here, and I've got a couple of minutes left before we finish, so I think it's time we did some demo stuff, right? See what we can do with this. I'm going to move over where I can see the screen. So we've got a disk drive. I could do DIR. I can see what's on my disk drive. We've got various different text modes we can support. So type mode, these are all the different modes that are available. We've got audio. We've got loadable programs. Let's do the loadable programs first. So if I go load, hello.elf, I wrote an elf loader. Nobody'd written a no standard elf loader before because that's not a thing. Who needs one of those? Well, I need one of those, so I wrote one. So there's an elf file on disk, and I've parsed it, and I've basically flashed the RAM using the contents of the elf file, and then I can just type run, and we can just run the program. So, you know, that works. We can load programs. We also have a couple of programs which I've stored into ROM, because sometimes the SD card isn't there and I've left it in the Mac or whatever. So now I can store programs in the ROM, such as this classic demo, which I think we saw at a previous RustConf. So that's still working, so that's good. So unlike previous versions of this demo, this is now built using ANSI graphics. I'm generating ANSI escape sequences to move the cursors around and set all the colors. And that means this demo source code will compile unchanged for Mac, Windows, or Linux, so you can actually debug it in your own terminal. The previous system I built was all kind of custom and exotic escape codes, but it's all kind of standard ANSI stuff now. So that's really nice. We've got audio, so it's kind of a cheat, this, because I've got an SD card. The processor's not fast enough to do MP3 playback, but when you've got an SD card, you can just store raw, uncompressed WAV files on disk, and so hopefully, we'll build a music player as well. Don't ask me how old that song is, because it depresses me. Bought that album when it came out. So I got one final demo for you, because I thought playing the WAV files is kind of cheating, right? Old-fashioned computers, they didn't have that much disk space available. Raw, uncompressed WAV files is just ridiculous. What we had when I was a kid was the Commodore Amiga, and it had these kind of very chunky chip tunes that it could play that were kind of formed around how the Commodore Amiga was designed. You had 4 channels of music, and it didn't have a synthesizer. You had to load the samples in memory and play the samples. And there was this great scene of people ripping off each other's songs and stealing the samples and remixing stuff. So I wanted to see, can you write a Rust program for no STD Rust that can parse one of these old-fashioned Amiga chip tunes and get them to play? Well, let's see if we can load this. One more thing for the demo to work. I can't see what I'm typing on screen because this screen is overscanned. So got to remember what I called it when I wrote it this morning. Excellent, that's loaded. So if I type this correctly, again, I can't see what I'm doing. This will be the end of the demo. So as it loads up, we've got our text mode. We've got our 4 audio channels. We've got all of the samples on screen. Of course, he didn't name the samples properly. He just shouted out to all of his mates, whoever wrote this tune. But this is it. This is what we've got. Thank you very much for watching.